Ever wonder what separates a perfect metal part from, well, a piece of scrap? It's not magic, I can tell you that. It's all engineering. And in the world of sandcasting, success or failure is actually decided long before any metal even gets melted. It really all comes down to design, and today we're going to dig into the key principles that turn a bucket of molten metal into a flawless, functional part. Okay, so look at this. This is literally the difference between success and failure. On the left, you've got a sound casting. It's accurate, it's strong, it's exactly what you want. But on the right, that's what happens when things go wrong. We're talking about porosity, tiny little voids inside, stress cracks that could break the whole thing, or even impurities trapped inside. And these aren't just ugly little blemishes. These defects can cause catastrophic failure. They're the kind of things that are a total nightmare for engineers.
So, the big question is, how do you make sure you get a perfect casting every single time? Well, it's not about luck. It's about making a series of really smart, deliberate choices way at the beginning of the process. And it all starts with the design of the pattern.
Yep, our first line of defense against all those defects is the pattern. You can think of it as the blueprint for the final part, but it's actually way more than that. It's a strategically modified version of it. This is the tool that's going to form the empty space in the sand, so every single detail here has a massive impact on the final result.
Here's the secret. A pattern is never an exact one-to-one copy of the final part. You have to build in what are called pattern allowances. These are super clever adjustments that basically predict what the metal is going to do. As metal cools down from liquid to solid, it shrinks, it changes shape. These allowances are how we design the pattern to account for all those changes right from the get-go.
There are three really critical ones we need to talk about. First, to fight that shrinkage, we just make the pattern a little bit bigger than the final part. Simple enough. Second, to make sure we can pull the pattern out of that delicate sand mold without the whole thing collapsing, we add a tiny taper to the sides. That's called a draft angle. And finally, for any surfaces that need to be perfectly smooth, we add a little extra material, a machining allowance, that'll get milled off later for a perfect finish.
And don't underestimate these little details. A tiny draft angle of just 2 degrees might seem like nothing, right? But it can literally be the difference between a clean pull and a total mold collapse. It's a perfect example of how getting the design right up front saves you from disaster down the line.
All right, next up is the mold itself. It's really easy to just think of it as, well, sand. But in casting, this sand is actually a highly engineered material. It's been specifically designed to create the perfect home for thousands of degrees of molten metal. So when you're choosing your sand, you have a major trade-off to make. Fine grains will give you a beautiful, smooth surface finish because they pack together so tightly. The downside? They also trap gases. Coarser grains, on the other hand, leave a rougher surface, but they create little pathways for all those hot gases to escape. So what you choose really depends on what's more important for the final part, a pretty surface or rock-solid internal strength. And that ability for gas to escape, it's got a name: permeability. See, when that super hot metal hits the sand, it instantly creates a ton of gas. If that gas has nowhere to go, it gets trapped inside the cooling metal, creating bubbles and voids that make the part weak. So high permeability is your best friend when it comes to preventing these nasty gas defects. Of course, sand on its own isn't going to hold any shape. It's just sand. That's where chemical binders come into play. You can think of them as the glue that holds all the sand grains together. They harden the sand into a strong, rigid mold that can actually stand up to the intense heat and pressure of all that liquid metal. The hotbox process is a perfect example of this. You take a mix of sand and binder and you blow it into a heated pattern. That heat kicks off a chemical reaction and boom, the binder cures almost instantly. We're talking about getting a solid, hardened core in as little as 10 to 30 seconds. It's a pretty amazing mix of chemistry and high-speed manufacturing. Okay, so we've got our pattern, we've got our mold. Now for the most dynamic and maybe the most exciting part of the whole process, getting that molten metal into the mold. And you can't just dump it in there. It's all about controlling the flow with absolute precision. This is all managed by something called the gating system. This is basically the network of channels, like little highways and roads, that guide the molten metal from where you pour it into the actual mold cavity. The entire goal here is to fill that mold up smoothly, without any chaos or splashing around. And this right here is the critical difference. A good design creates a smooth, calm, laminar flow. The metal fills the mold gently from the bottom up, pushing all the air out ahead of it. A bad design? That creates a chaotic, turbulent flow, metal splashing everywhere, trapping air, and even eroding the walls of the mold itself. It's a recipe for disaster.
Honestly, turbulence is the enemy of good casting. It's the direct cause of some of our worst defects. Porosity from all that trapped air, oxide inclusions from the metal's own skin folding into itself, and even mold erosion, which is just sand getting washed right into your final part. You have to avoid it at all costs.
To solve that other big problem, shrinkage, we use a clever tool called a riser. Just think of it like a reservoir of extra molten metal. As the main casting starts to cool and shrink, it wants to create a void. Well, the riser, which is designed to stay liquid just a little bit longer, feeds extra metal back into that void, making sure the final part is completely solid and dense.
Now, all these principles are timeless, but the tools we use to apply them have been totally revolutionized. Let's take a look at how modern technology has completely changed the game, shifting the focus from fixing problems to just preventing them from happening at all.
The whole philosophy today is pretty simple. The absolute best way to fix a casting defect is to solve it digitally before it even has a chance to exist in the real world. So instead of a costly, frustrating cycle of trial and error, we can now find and eliminate problems inside a computer.
This digital workflow is a total game changer. You start with the 3D model, and you digitally add all those allowances we talked about. You design the whole gating system on the computer. But here's where the magic happens. You run a simulation that shows you exactly how the metal is going to flow and cool, and it flags potential defects before you've spent a dime on materials. You can tweak and perfect the design virtually, so that when you finally send the file to get the pattern made, you already know it's optimized for a perfect cast.
And the impact of this is just enormous. Using these simulation programs means we can dramatically cut down, or sometimes even completely get rid of, the expensive and time-consuming physical prototyping stage.